Hello everyone. In this lecture I shall discuss two important problems based on the Kuntukar conditions. In problem number 1, we have two inequality constants. Okay. In problem number 2 we have the transcendental functions, right? So now before the details of the solution of problem 1 and 2, let me introduce myself. Myself Professor Susanta Kumar Paikray, currently working as a Professor of Mathematics at Veer Surendra University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let me to solve these two problems. Coming to solution of problem 1. Solution of problem 1. We consider the Lagrangian function. Right, consider the Lagrangian function. Consider the Lagrangian function. L is equal to here z minus means here 10x1 plus 10x2 minus x1 square minus x2 square minus here lambda times the first constant left hand side minus right hand side x1 plus x2 minus 14. This is lambda 1 times minus lambda 2 times the second constants here minus x1 plus x2 minus 6. Right, so coming to the necessary conditions. Necessary condition. You have two decision variables. So first one is Lx1 is equal to 0, then Lx2 is equal to 0. So what is Lx1? We differentiate with respect to x1. So that means what we are getting? We are getting 10 minus 2x1 minus lambda 1, and it is minus minus plus lambda 2 is equal to 0. And coming to the second, in differentiating with respect to x2, it is implies 10 minus 2x2 minus this is lambda 1, this is minus lambda 2 is equal to 0. Okay, and the next constants, next is here lambda 1 h1 is equal to 0, next is lambda 2 h2 is equal to 0. So lambda 1 h1 is equal to 0 means lambda 1 times x1 plus x2 minus 14 is equal to 0, this one. Then next this one implies here lambda 2 here minus x1 plus x2 minus 6 is equal to 0. Next the given conditions, here x1 plus x2 less than is equal to 14 minus x1 plus x2 less than is equal to 6. This is here condition 1, this is condition 2, this is condition 3, this is condition 4, this is condition 5, this is condition 6. Now we have regarding lambda 1 and lambda 2. What happens to your lambda 1 and lambda 2? You see here the problem is of maximization type and the constants are less than equal. Maximum with less than sounds opposite here. So sounds opposite means it's positive, greater than is equal to 0. It is my 7th. So next is x1 x2 is greater than is equal to 0. This is my 8. So these are 8 constants. So since we have lambda 1 and lambda 2, right? So there are 4 possible cases, right? So from equation 3 and 4 we have 4 possible cases. 4 possible cases. So the cases are case 1 lambda 1 equal to 0, lambda 2 is equal to 0. Case 2 lambda 1 not equal to 0, lambda 2 equal to 0. Case 3 lambda 1 equal to 0, lambda 2 not equal to 0. And case 4 here lambda 1 not equal to 0, lambda 2 not equal to 0. So let us solve this problem under 4 cases, considering here case 1, right? The case 1 is lambda 1 is equal to 0, lambda 1 equal to 0, lambda 2 equal to 0, right? So now equation 1 follows. Equation 1 follows. Since here lambda 1 is equal to 0, you substitute it here. 10 minus lambda 1 and lambda 2 both are 0. So here 10 minus 2x1 equal to 0. 10 minus 2x1 is equal to 0. Implies here x1 is equal to 5. And here equation 2 follows. Equation 2 follows. Here 10 minus 2x2 is equal to 0. So this implies x2 is equal to 5. So we are getting x1 and x2 greater than equal to 0 here we are getting. Right, this x1 and x2, this is greater than equal to 0 we are getting. So now equation 7 and 8 satisfy, right? So because we are taking this lambda 1 lambda 2 positive and this positive, so here equation 7 and 8 holds. And here 1 2 3 4 is by default. Okay, 1 2 3 4 is by default, no need to check, it will satisfy. Only thing we have to see 5 and 6, right? To check 5 and 6, to check 5 and 6. Okay, so from 5 what we have? X1 plus x2 less than x1 plus x2 is equal to 5 plus 5, which is less than is equal to 14. True, right? True. So 5 holds, and from equation 6 we have minus x1 plus x2, right? So this is 0, minus 5 plus 5, which is less than is equal to here, less than is equal to 6 holds, right? True. So that means 6 holds. Clearly all conditions 1 to 8 hold under case 1, right? Next thing we have to see, right? Next thing we have to see here the sufficient condition. At last we will see to NCR maximum. We will do it. Okay, at last we will do after all steps. Now coming to your case 2. In case 2 you have lambda 1 equal to 0, lambda 2 not equal to 0, right? So lambda 1 is equal to 0 implies here equation 1 gives you. So from equation 1 you have 10 minus 2x1 minus lambda 1 is equal to 0. From equation 2 you have 10 minus 2x2 minus lambda 1 equal to 0. If you subtract it, minus plus this and this cancelled. So what we are getting? So this implies my minus 2x1 plus 2x2 is equal to 0. So this implies here x1 is equal to x2, right? X1 is equal to x2. Now from equation 3 here lambda 1 is not equal to 0. So that means lambda 1 is not equal to 0. So that means this is 0. x1 minus x2 is equal to x1 plus x2 is equal to 14. x1 plus x2 is equal to 14, right? So if you substitute this here, so 2x1 is equal to 14 implies x1 is equal to 7. So x1 is equal to x2. So x1 is equal to x2 is equal to 7, right? x1 is equal to x2 is equal to 7. Now this lambda 2 is not equal to 0, lambda 1 equal to 0. Now we see what is the value of, actually it is lambda 1 is not equal to 0, sorry, this is lambda 1 is not equal to 0, lambda 2 equal to 0. Okay, so that's why lambda 1 is there. Now to find lambda 1, from equation 3, from equation 1. Okay, from equation 1 you have 10 minus 14 minus lambda 1 equal to 0. So that means lambda 1 is equal to minus 4 is negative, right? So lambda 1 is negative here. So here condition 7 fails, right? So this implies condition 7 fails. So therefore case 2 doesn't work under KKT condition, Now come to your case 3, right? Under case 3, lambda 1 is equal to 0, lambda 2 not equal to 0, right? So from your equation 1, what you are getting? 10 minus 2x1 plus lambda 2 is equal to 0. From equation 2 we are getting 10 minus 2x2 minus lambda 2 is equal to 0. If you simply add it, this and this cancelled. So this implies here x1 plus x2 is equal to here 10, right? So let it be my equation A. Next from equation 4, right? Here lambda 2 is not equal to 0. You see, this is my equation 4. Lambda 2 is not equal to 0 means this remaining minus x1 plus x2. So this implies you have minus x1 plus x2 is equal to 6. Let it be my equation B. So now we solve A and B. Solving A and B, right? x1 plus x2 is equal to 10 minus x1 plus x2 is equal to 6. If you simply add it, here 2x2 is equal to 16. So that means here x2 is equal to 8, right? With x2 is equal to 8, here x1 is equal to 2. So this implies x1 is equal to 2, right? Now we have to find the value of lambda 2. For lambda 2 from equation 1 you have 10 minus 4 minus 0 plus lambda 2 equal to 0. So that means lambda 2 is equal to minus 6. So you see here condition 7 fails here, right? So here condition 7 fails here because we need positive. So here condition 7 fails. So this implies condition 7 fails here. So therefore case 3 doesn't work under KKT condition. So now come to here case 4. In case 4, here lambda 1 is not equal to 0, lambda 2 is not equal to 0. So if this is not equal to 0, so now from 3 and 4 you have this 0 and this 0. From 3 and 4 we have x1 plus x2 is equal to 14 minus x1 plus x2 is equal to 6. If you solve it, here 2x2 is equal to 20 implies x2 is equal to 10. With the value of x2, here x1 is equal to 4, right? X1 is equal to 4. Now from 1 and 2, here 2x2 minus lambda 1 plus lambda 2 is equal to 0 minus 10 minus lambda 1 minus lambda 2 is equal to 0. Simply if you add it, right, what you will get? Here lambda 1 is equal to minus 4, lambda 2 is equal to minus 6. So what we conclude here? This lambda and lambda 2 we are getting negative, right? So condition 7, that is right, condition 7 fails. So we reject this case. Now to confirm the maximum under your case 1, we have to see the sufficient condition, right? We have to see the sufficient condition. So what is your f? F is your z. What is your z here? Your z is equal to 10x1 plus 10x2 minus x1 square minus x2 square. So what is zx? Zx1, it is 10 minus 2x1, and what is z? x1 is here minus 2, right? Then similarly, what is your z? x1 x2 is 0. Similarly, what is your zx2? Zx2 will be here 10 minus 2x2 implies z x2 x2, so minus 2, and what is your zx2 x1 is here 0. So therefore, what is my Hessian matrix? Hessian matrix Hx is equal to zx1 x1, zx1 x2, zx2 x1, zx2 x2, right? This is the matrix, Hessian matrix. What is my d1 now? My d1 is equal to, so what is it? So it is here 0 minus 2 0 minus 2 matrix. Sorry, this matrix here is, this is your minus 2, this is your minus 2, and this is your 0. So what is your d1? D1 is this only. So this is minus 2, here negative. And what is d2? It is determinant, the second order principal minor, minus 2 0 0. Determinant, this is equal to 4, this is positive. So alternatively it is negative and positive, so it is negative here. So Hx is negative definite. Okay, negative definite. Negative definite leads to your concave, right? That is f is concave. So that means f ensures maxima with respect to your case 1, right? So your z is concave, so z ensures your maxima under case 1. So what is the maximum value now, right? So therefore my z max is equal to z at the point under your case 1. Under your case 1, what is the value? x1 5 and x2 5, right? Here x1 5 and x2 5, 5. With this, what is the value of z? If we solve it, it will give you here z is this 50 plus 50 minus 25 minus 25, 50 plus 50 minus 25 minus 25. So this cancel is equal to your 50. Okay, so therefore z max is equal to 50 at your extreme point. X star is equal to your 5. Okay, so this is the answer. So this is the optimal solution. Which is the optimal solution? Optimal solution. Now coming to the solution 2. So now coming to the solution of this, let my L is equal to z minus means minus log x1 minus log x2 minus lambda times here x1 plus x2 minus 2, right? Now coming to the necessary condition, KKT condition, right? Here two decision variables, Lx1 is equal to 0, Lx2 is equal to 0, lambda h is equal to 0, right? And here h less than is equal to b, right? Here g, h less than is equal to 0 means g less than is equal to here b. Okay, what is your lx1? If you differentiate it, so that means it is minus 1 by x1 minus lambda 1 is equal to 0, and this implies here minus 1 by x2 1 by x2 1 by here x2 minus lambda 2 is equal to 0. So lambda h is equal to 0 implies lambda times x1 plus x2 minus 2 is equal to 0. H negative means whatever given x1 plus x2 less than is equal to 2. So let it be my condition 1, this is condition 2, this is condition 3, this is condition 4. Now you see here, this is minimization and it is negative. It sounds, it is less than, minimize and less, it sounds same. Sound same means lambda is negative. So lambda is negative here. This is condition 5. Then your next condition, here x, here x1 x2 is greater than is equal to 0. It is your condition 6. Okay, since we have one lambda, right, there arise two cases here. In view of this lambda, we have lambda not equal to 0 and here lambda equal to 0. Case 1 and case 2. There arise two cases. Case 1. Okay, case 1. Let lambda is equal to 0. If lambda is equal to 0, then from equation 1 and 2, right? From equation 1 and 2, minus 1 by x1 is equal to 0. From equation 1 and 2, 1 by x1 is equal to 0 and 1 by x2 is equal to 0. So what does it mean? It means x1 tends to infinity and x2 tends to infinity, right? x1 and x2 infinite. Now what happens to my 4? So this 4 is violated, right? So thus equation 4 is violated. Therefore we reject this case. Okay, next come to here case 2. Let lambda not equal to 0. If lambda not equal to 0, right, then from equation 1 and 2, from equation 1 and 2, what you are getting? First you come to equation 3. Lambda not equal to 0 means this is 0. From equation 3, right? From equation 3, you have here x1 plus x2 is equal to 2. From 1 and 2, x1 is equal to minus 1 by lambda and x2 is equal to minus 1 by lambda. Okay. Now if you substitute this, okay, so if you substitute this here from equation 3, here 2 by lambda, right, minus 2 by lambda is equal to 2, right? So this implies 2 lambda is equal to minus 2. So that means lambda is equal to my minus 1. Lambda is equal to minus 1. So lambda is negative here. Equation 5 holds. Now what happens to? So this implies equation 5 holds. So let us find x1 and x2. Now you see it is lambda only. It is only lambda. Why 1? It is lambda only. Okay. So now from equation 1 and 2, right, what you are getting? Now from 1 and 2, you have x1 is equal to 1 and x2 is equal to 1. Okay, x1 1 and x2 1. So the last condition 6 holds. that is 6 holes, 5 and 6 holes, right? 5 and 6 holes, and these are all verified earlier. Clearly all 6 conditions holds, right? Clearly all conditions 1 to 6 hold, right? So now to ensure the minimization, we have to check the sufficient condition. Come to the sufficient condition. What is your Hessian matrix? What is your Hessian matrix? Your Hx is Z x1 x1, Z x1 x2, Z x2 x1, Z x2 x2. So now if you take the Z x1 x1, right? Z x1 x1, this is my Z. The derivative with respect to x1 is minus 1 by x1, so it is 1 by x1 square, right? It is here 1 by x1 square, and it is here 0. It is here 0, 1 by x2 square, right? So what is my d1? d1 is 1 by x1 square, since it is a square function. So this is your positive. And what happens to d2? d2 is the determinant of the whole matrix, 0, 1 by x2 square. So this is 1 by x1 x2 square. So this is also positive. So this is positive. Both are positive. So Hx is positive definite. Positive definite. So that means Z is convex. Now what happens to your G? Next, G being linear, right? G being linear. G is what here? x1 plus x2 less than is equal to 2. This is linear. So this is both convex and concave. So G is here, this is convex, means we need concave. Therefore here Z is minima. Z is minimum at here x1 is equal to x2, at x star is equal to 1 1. Okay, with Z mean value is equal to minus log 1 is equal to 0, right? So therefore optimum value of Z is 0 at x1 is equal to 1, x2 is equal to 1. This is your answer. So to conclude, what we see, if all the constants are not equal sign, then we use KKT condition, but this KKT condition is lengthy. Okay, if m is equal to 1, only one constant, then here two cases. You have two cases. If m is equal to 2, then you have 4 cases, right? 1 2 3 4, 4 cases, as we did the first problem. Similarly, if m is equal to 3, then there are 8 cases. So this problem will quite lengthy, right? Now to avoid this, we have here Wolff's modified simplex method. It is a simplex like technique with some modification, and Beal's method. The Beal's method is algebraic procedure. Okay, so now both the methods to work, we need the objective function. Objective function is quadratic plus linear. This is the restriction here, right? And the constants are linear. Okay, so in the upcoming lecture I shall discuss this Wolff's method and Beal's method, right? In upcoming lecture we should focus on these two methods, Wolff's method and Beal's method, right? So till now, at this stage, my appeal to all of you is that If you think that this lecture is useful and interesting, please like and subscribe to this channel, which will boost my motivation to upload subsequent lecture for your benefits. So thank you all. Have a nice day.